In this video, we'll study how to find the Laplace transform of functions. By definition, the Laplace transform of a function f of t, written now with the conventional square parenthesis for Laplace transforms, is the integral from 0 to infinity of f of t e to the minus alpha t dt. Because the exponential function, decaying exponential, decays faster than any polynomial, this integral is always guaranteed to exist for a large class of functions. So, as an example of finding the Laplace transform of some functions, let us try finding the Laplace transform of t to the power n. So in other words, let f of t be equal to t to the power n. Then L of t to the power n is going to be the integral from 0 to infinity t to the power n e to the minus alpha t dt. This type of integral can easily be evaluated using the method of integration by parts. What you can do is to call this integral first of all something. So in order to evaluate this integral, let's call the integral I sub n equal to the integral of t to the power n from 0 to infinity e to the minus alpha t dt. Let us call this variable u, and let's call this variable dv. The method of integration by parts should be followed. So du will give me n t to the n minus 1 dt, and v is going to be negative 1 over alpha e to the minus alpha t. Applying the recipe of integration by parts, which is that the integral u dv is uv minus the integral v du, I will get negative t to the n over alpha e to the minus alpha t from 0 to infinity, minus of minus, so that's plus, v du, so that's n over alpha, the integral of t to the n minus 1 e to the minus alpha t dt. In evaluating this integral, let's look at what happens at infinity. I already mentioned that the exponential function decays faster than any polynomial, so the value at infinity is 0. The value at 0 is also 0 thanks to t to the power n, so this makes no contribution whatsoever. The only contribution you have is n over alpha times, coincidentally, the integral in minus 1, because it's the same as in except with t replaced by t to the power n replaced by t to the power n minus 1. So continuing this process, I'm going to keep getting n times n minus 1, in minus 2, and then n minus 2, in minus 3, and then I'll get a value up to 2. So it's going to be 2 minus 1, which is I1, and then 1 times I0. Meanwhile, I have alpha multiplying all of these things. So there's going to be 1, 2, 3, n factors of alpha, so that's alpha to the power n. Okay, now I will tell you a little bit about this variable alpha. It's usually called something else. It's usually called by the variable s, but we'll fix that later. So this is going to give me that. Now all I need to do is do an honest integral, which is I naught, and that's easy to do because t to the power 0 is 1, and that's just e to the minus alpha t dt, which is negative 1 over alpha e to the minus alpha t. At infinity, this integral vanishes, so I get negative 1 over alpha, 0, and at 0 it's just 1. So this integral is just 1 over alpha. So if I put everything together, I get in equals n over alpha to the power n plus 1. N factorial, excuse me, because n times n minus 1 times n minus 2 is called n factorial. So that's how you can find the Laplace transform of different functions. You actually explicitly calculate the integral, and a lot of these are in your homework assignment, so you can get practice applying this formula for different kinds of functions. Now back to nomenclature. I did say that Laplace transforms are usually not declared with variable alpha but with variable s, and so the engineering literature defines your Laplace transform as integral 0 to infinity f of t e to the minus st dt. So the variable s is used for all the Laplace transform. In other words, the function g is a function not of alpha but of s. So let us use this to our advantage using the convolution theorems next. So in exactly the same manner, you can show, just as we showed for this one, the Laplace transform of t to the power n is n factorial over s to the power n plus 1. You can also show that the Laplace transform of sine at is equal to a over s squared plus a squared. Now, what if I had a product of these two functions? So we are now going to be thinking of convolution. So suppose I had a function called h of s, which is a product of these two things. So it's a over, let's say, something like s squared times s squared plus a squared. So you know that separately, you secretly know that the Laplace transform of t is going to be t to the power 1 is going to be 1 factorial, which is just 1 over s squared. So you know that s squared factor can come like that. So you also know that the Laplace transform of sine at is going to be a over s squared plus a squared. So you also know that a over s squared plus a squared can come like this. But these are products of two Laplace transforms. So in other words, h of s is the product of the Laplace transform of t times the Laplace transform of sine at. So if I want to find a single function of which this is a Laplace transform of, then I said of twice, so of which this is a Laplace transform, then I would have to say let this be the Laplace transform of some mystery function h of t, which we still have to find. Now, by the convolution theorem, the Laplace transform, if I have to find the Laplace transform of this would be the function h of t would then be the inverse Laplace transform of the product of two Laplace transforms. So it would be the convolution of the two. So it's going to be integral 0 to t of the convolution. Now I have a choice. I can put t, I can make the variable t minus tau, or I can make this a of t minus tau. I'm chicken, so I decide to put the t minus tau on that one. By the way, it can be done on either one because of the symmetry property of convolutions. So I get sine a tau d tau. Okay, this follows from the convolution theorem. All right, now that we have this, it's just a matter of evaluating this next. This is just another integral. Fortunately for us, it's very easy to evaluate this integral. I can break it up into the sum of two integrals. So I get t times, because t here is a constant as far as the variable tau is concerned, 0 to t sine of a tau d tau minus integral 0 to t tau sine of a tau d tau. So the first integral is easy to evaluate. It's just negative t over a cosine a tau, because the derivative of cosine is negative sine. The negative sign cancels and you get back that. So that's 0 to t, minus, here you have to use integration by parts. So we're going to call this a u function, and we're going to call this the dv function. So let's do the integration by parts once again. So that's going to be u times v. So that's negative, v is just like that. So I'll just copy down that result there. Tau over a cosine a tau from 0 to t, plus, because minus of minus is plus, integral v du. Du is just d tau. So that's going to give me the upper limit contributes, the lower limit doesn't contribute. So I get negative t over a cosine at. That's a minus of minus, so that's plus. At the upper limit, I'm going to get t over a cosine at. So those two things cancel out. At the lower limit, I'm going to get negative 0, because the tau, well, actually, wait, sorry. At the lower limit, tau is a variable, so that's 0. And then I have this one, that integral. So that still needs to be done. So it's going to give me negative. The integral of cosine is just sine. So that's going to give me negative 1 over a squared sine of a tau between 0 and t. Sine only contributes in the upper limit, not in the lower limit. So this gives me negative 1 over a squared. And there's something that I'm not doing right. I'm trying to figure out what it is. Okay, I think I narrowed down my mistake. I forgot the lower limit here. The lower limit here that only affects tau. It doesn't affect t. So the lower limit is still there. So that gives me minus of minus or plus t over a. So I get t over a. Forgot that the integration is only over tau and not over t. So that's the mistake I made there. These things are very tricky. Always check your work. T over a, and then I have, that one is just negative 1 over a squared sine of a tau, at. When tau is 0, that's going to give me sine of 0. So that's the Laplace transform. That's the function of which the Laplace transform is that. So that's what you may call the inverse transform. So this is sometimes called the inverse transform of h of s. And if you like to write things in common denominator form, it's going to be at minus sine at over a squared. These types of calculations are extremely useful, and this illustrates the utility of the convolution theorem. So the product of two functions, when you want to find the Laplace transform of that, it's going to be the integral or the convolution of those two functions, as we learned in one of the convolution theorems. So this property is going to be used again and again while using Laplace transform technique to solve ordinary differential equations.